Hi guys, let's get something interesting displayed on the screen using the SCN2674. There's a lot to get through, but I'm going to do this step by step, explaining what's going on and verifying things as I go, and as always let me know in the comments if you have any questions. In the last video, this is where we ended up. This is the SCN2674 Advanced Video Display Controller, and we have a 25.175 MHz oscillator divided down by a 4-bit counter to feed it a character clock signal at about 3 MHz. Its data bus is connected to a 6502 system through a 6522 so that we can initialize it and send it commands, and I've connected the VGA output here to a small LCD monitor. The only signals going to the monitor at the moment are the horizontal and vertical sync signals through these two wires, and when I turn it on the monitor blanks and we can see that it's receiving a 640 by 480 60 Hz signal as expected. So what does it take to get something actually displayed on the screen? Well, we need to send some data to the RGB lines, which are currently not connected at all, and as you've seen in my other VGA output videos, it's important to only send data during the active portion of the frame, because monitors use the levels during the blanking period to establish a black reference voltage. So it's important that we output black in those periods. The SCN2674 provides us with a blank output that we can use for this purpose, but we can't just connect it straight through to the RGB lines because the polarity is wrong. It's low during the active period and high during blanking. So I'm going to put a quad NAND gate here and start by using one of the gates to invert the blank signal, and that should result in a white display. So I'm going to add a decoupling capacitor, power and ground, join pin 1 to pin 2 so this first gate functions as an inverter, and then connect the blank output to pin 1, and after reconnecting the VSync and HSync signals, I'll finally connect this inverted blank signal to the RGB resistors going through to the VGA connector. Turning this on then, we get a clear white screen as expected. Great. I can actually see here that the left edge of the screen isn't in the right place, which probably means the VGA timings aren't quite right, and that's something I'll try to correct a bit further down the road, not this time though. So if we want to display something more than a white screen, there are lots of interesting timing signals already available to us, but we can't just use them directly, we need to gate them with this inverted blank signal so that they don't output during the blanking intervals. And that's why I use the quad NAND here rather than just an inverter. We can feed the output of that first gate into another gate here, and then NAND it with whatever signal we want to. And the result of that's going to come out inverted again, so I need to feed that back through another one of the NAND gates to invert it back again. So now we have the blank signal being inverted, then NANDed with some other signal we can choose, and then inverted again before going to the RGB outputs. I'll also add a pull down resistor here to avoid display flicker when I'm moving this floating connection around by hand. So now if we turn this on again, we still expect a black screen due to the resistor, as we haven't connected a signal yet. And let's connect the signal to the power rail first, and we get a white screen, which is good. Now we can try the carry output from the counter. This lights up every 16th pixel, which is expected, and the fourth output bit of the counter is also interesting, as this lights up alternating stripes of 8 pixels each, and that's interesting because this is going to be our horizontal character resolution. It matches the clock signal going to the SCN2674. We can also try higher frequency signals from the counter to get denser stripes, and its first output bit alternates every pixel, so this is the highest resolution we can display on a 640 by 480 monitor. There are also interesting outputs on the SCN2674. While it scans across the screen, it is outputting incrementing addresses. Effectively it's dividing the character clock down again and again to form those addresses. So the low address bit here gives us that pattern of 80 stripes again, and the next address bit halves that down to 40 stripes. But note this weirdness in the top left corner here. So before we go on, let me explain what that is. The SCN2674 has 14 output pins for outputting display addresses, DAD0 to DAD13, but there's more timing information it wants to output, especially a lot of signals that remain constant during each scan line. To avoid needing a larger package with more pins, these additional signals are just multiplexed onto the same address pins. So at the moment when the blank output goes low, the address pins actually contain this secondary data rather than the true address data. Here in the datasheet you can see that DAD0 also carries an LG signal. DAD1 carries the signal for DAD14, and so on. I'm not totally sure how DAD14 and 15 work, because in theory they're not actually constant during the scan line, but the rest of these signals that are listed here are constant. What we're currently seeing in the top left corner then is the DAD14 signal, which ought to be off all the time for us, but something weird is going on with that top line of the display that I'm going to have to look into another day, as we have more exploring to do now. So looking ahead down the list here to see what we can watch out for in a moment, we have the last row signal, which indicates the final character row on the display. We have 4 line address signals, which are going to be very important for us. They indicate the scanline address within each character row. There's a first line signal that indicates the first line of each character row. A double width signal, which shows whether this row should be rendered double width. An underline signal that indicates which line within a character row should be used for underlining. A blink signal that says whether blinking text should be on or off this frame. An odd field signal that's used on interlaced displays to tell which of the two fields is currently being output. And a last line indicator that indicates the last scan line of each character row. So we can watch out for those as we go. So the next pin along is DAD2, and we have 20 stripes. And then DAD3 gives us 10 stripes, and the left column is now indicating the last row of the display, as you can see. Then we have 5 stripes, which is interesting because now it's an odd number, so we can see alternating colours in horizontal stripes as well. These stripes are 128 pixels wide. The left column is also indicating the bottom bit of the scanline number, so it alternates on every scanline. Moving along more, this is now 256 pixel wide stripes, which don't evenly divide 640 at all. And then we have 512, 1024, 2048, 4096, 8192, and 16384. And now this left hand side is steadily flashing, and this is the blink signal that's used for controlling blinking text on the screen. Then we have 32,768 pixel wide stripes, and the left side is flashing on and off every frame now, and I think this is the odd field signal. It's interesting because we're not meant to be outputting an interlaced signal here, so this is kind of redundant. I'm not sure why it's actually happening. And the last pin along is now black for the whole display, and the left column is indicating the last scan line of each character row. So there's all the signals coming out of the SCN2674. Going back to the first one again, we have 80 stripes across the screen, which is for now going to be our character resolution. And then this one here shows what our vertical character resolution is going to be. Again, 8 pixels per character. I think that's 60 rows on the whole screen. So how do we draw actual characters on the screen? Just like in my custom VGA circuit, to draw anything higher resolution than the character clock, we're going to need to use a shift register. The idea is we load up the shift register once per character clock, and then use the VGA pixel clock to shift the shift register along and change which of the bits we loaded is being output. So let's run some quick tests of that. This is a 74HCT166 shift register. It's a parallel in serial out shift register. I'll straighten up the pins and put it in the right side over here near the output connector. It ought to have a decoupling capacitor, of course, and power and ground connections. Pin 1 is the serial input pin, the value that gets shifted into the register, and we want to wire that low so that it outputs black when it's idle. Pin 7 is a clock pin, which goes to the main VGA clock. Pin 6 is a clock enable pin, and we want that to be low all the time so that it's always enabled. And pin 9 is an active low reset, which I want to wire high so that it's not resetting. Pin 15 is a tricky one. This is the parallel enable pin, which causes the register to load from its parallel inputs instead of shifting when the clock ticks. And we need this to go low either side of just one clock pulse out of every 8, and that's kind of hard to arrange here. For now, I'm going to connect it to the carry output of the counter and see what happens there. Most of the rest of the pins are parallel input pins, and I'm going to hardwire those in an alternating pattern first of all, just for test purposes, so we can see something on the screen. So turning this on now, we get the same pattern as before, but we can now move the pixel input wire to the shift register's output and see what we get. And it's a pattern of white lines, looks like 16 pixels apart. So that's a bit weird. Let's move the parallel enable input across to one of the other counter outputs. So we can see now the 8 bits of the shift register data appearing, followed by 8 pixels of blackness because we keep reloading it on every pixel during that period, and that's just because that parallel enable signal isn't correct. So timing the parallel enable signal is obviously more complex than this, and for my prototype, which I showed in a short video last week, I built a circuit up from inverters and flip-flops to make this pin go low for just one cycle out of every 8. But that was quite messy and it didn't work very well. And doing all of that from scratch isn't really the point here. We're already using a monolithic controller IC. So unlike for my home-built VGA project, I decided to just simplify things here by using a PLD to generate this signal. It's a 16V8 GAL and it will save a lot of trouble and provide some flexibility that I can already see we're going to need in the future if we want to get the VGA timing more correct, because we can work around some of the limitations of the SCN2674 in the GAL. I'm using it in registered mode, so almost all of the outputs will change synchronously with the VGA clock, which comes in on pin 1. I'm also duplicating that clock input on pin 2, so that I can invert it asynchronously, as I'll need that later on. I'm also feeding in the blank, VSync and HSync signals from the SCN2674. I'm going to use the GAL to invert them all, because VSync and HSync ought to be inverted. I hadn't done that up to this point, and most monitors don't seem to care, but according to the spec they should be the other way up. And this is also to ensure that they all change synchronously at a constant time during the clock cycle, because the SCN2674 has very loose margins for all these signals. They're spec'd to change up to 5 VGA pixels after the character clock ticks, which is really unacceptable. In practice it probably is more predictable than that, but I want to have more control over it, so I'm going to latch them here. On the output side then, in addition to the inverted clock, blank, VSync and HSync signals, I have the shift register's parallel enable signal and 3 counter bits. And the GAL is going to completely replace the 4-bit counter I already have in the circuit. The third counter bit forms the character clock for the SCN2674, just like it did with the old counter IC. I won't go into detail on the way the logic is written, but it's on the screen if you're interested, and please do ask, as always, if you have questions about it. One thing I will say though is that although I'm using WinCouple, its GUI is really unstable, so I prefer to just edit the files in a text editor and run it from the command line. And yeah, you can do that. If you look up the documentation you can see how to do that, and I have a script that kind of wraps that up, and it compiles the PLD code and runs the simulation to test the results, and deals with all the command line arguments and things like that, and prints out any errors, which is really convenient. Speaking of simulation, I filled in a lot of test cases in the simulator input file. It's a bit tedious to do, but this was really valuable as it highlighted some problems with my PLD code that needed to be fixed before putting it in the circuit for real. One day I might try to learn how to write the test cases more concisely, but it was definitely worth it, even though it was a bit of a hassle. Anyway, with that all sorted out, I programmed the PLD using my TL866, same as I used for EEPROMs. So we can now remove the counter and NAND ICs from the breadboard. I'll start with the counter, and I'm going to have to move the oscillator along a bit too, as the PLD is wider than the counter was. It's got more pins. So the clock goes in on both pins 1 and 2. Pin 11 needs to be grounded as it's an output enable pin. And I'll also short these unused inputs to ground on pins 6, 7, 8 and 9. The character clock goes from pin 19 here over to the SCN2674. And I also need the blank VSync and HSync signals from the 2674 to come back to the bottom row inputs here. And I can connect the sync signal outputs from the PLD through to the VGA connector. So let's turn it on now and check that the PLD is driving everything it should be so far. This is important because it's integral to the system now. It's providing the character clock and it's also processing the sync signals, so it's an important test. And it looks good, so we can move on to the shift register. Its output can go straight into the VGA connector now, because in the PLD code I've arranged to only load data into the shift register when we're not blanking. So during blanking intervals it will keep shifting and end up all zeros, as its serial input is wired low. The shift register's parallel enable pin comes from the PLD of course, and its clock pin also comes from the PLD. I'm using the inverted clock for this so that it will rise in the middle of the PLD's regular clock cycle, rather than trying to trigger a shift of the shift register at a point where other signals, especially the parallel enable signal, might not be stable. While I'm here, I'm going to replace this long yellow wire with a shorter one, just because it's annoying, and it's still going to be going from the shift register output to the VGA color channels, just a bit tidier. So now we have the shift register's clock and parallel enable hooked up. Let's see what happens. And it looks good. The whole display is now filled with alternating black and white pixels, so it looks like the shift register and GAL are working completely as intended, and I think this really illustrates the value of taking the time to write the test cases for the PLD simulator, as the issues there would have been much harder to diagnose in an actual circuit. To demonstrate what the shift register is doing then, I can change one of its inputs and you'll see the effect on the display. I can take this bottom bit out and wire it low instead of high, and it'll leave a gap in the pattern once every 8 pixels. And then I can take another one out as well, so you can see that this pin affects a different one of the 8 repeating pixels. So now let's make it display something that's not exactly the same over the entire display. I'm going to remove the hard-coded inputs from the shift register and wire it to the low address bits from the display controller instead. And this means that each 8 pixel group on the screen will now show the binary representation of the low byte of the address that the display controller wants us to be presenting at that location on the display. So it's pretty easy to hook that up, and we now get this kind of barcode-like pattern, and you can clearly see a lot of repetition both horizontally and vertically. Making sense of the pattern, you can see here a sequence counting up through 0, 1, 2, 3 and so on up to 15. It's a little less clear beyond that, but as it continues to the right it counts through 16, 17, 18 and so on. And if you look carefully, you might also see that when you move down vertically, the count increases by hex 50, which is 80 bytes, as there are 80 characters horizontally across the screen. Also of interest is the left-hand column again, and this is the only part of the screen that's not replicated 8 times vertically. And that's because it's not actually showing character addresses there. What we're seeing there is the scanline address within the character. The first scanline of the character is line 0, and then line 1, then line 2, and so on up to 7. And the SCN2674 actually supports up to 16 scanlines per character, but I've only configured it to 8 at the moment. Let's look at the next step to getting text characters displayed. So instead of driving the shift register from the address lines, what we need to do is drive the shift register from the data lines of a character ROM. Each address in the character ROM will contain the bit pattern for one line of the corresponding character. The bottom 3 bits of the ROM address will specify which scanline of the character we want to fetch, and the remaining bits will specify the ASCII code for the whole character. To make this work, we're going to need those bottom 3 bits throughout the scanline. But remember that the SCN2674 only outputs them in that period just before the start of each scanline, so we're going to need to latch them into a register. And this is an 8-bit D flip-flop which latches its data when its clock pin rises. So I'll give it power, ground, and I'll connect the reset pin high as I don't need that. And I'll reconnect the shift register inputs to the D flip-flops outputs, and connect the D flip-flops inputs to the address lines of the SCN2674. So what this is doing is it's sitting in between the SCN2674 and the shift register in order to kind of latch these signals. And finally, the D flip-flop's clock needs to be triggered by the falling edge of the blank signal, so I'm going to connect it to the inverted blank signal that I made the PLD output earlier on. So now, instead of the pattern we saw before, we see the data from the left column replicated across the whole display. So that's great. We have what we needed and can now access that data at any point during the scanline. Now I think we're ready to actually get some text characters on the screen. I've programmed this EEPROM with the bitmap data for the main ASCII characters. I already had this in 6502 assembly form, so I just made a dedicated file to output the bit masks on their own with no actual 6502 code here. I'll connect the character ROM's data outputs to the shift register's parallel inputs and set up the main control signals on the EEPROM as well. The high address bits of the EEPROM need to be connected low because I didn't program anything into the higher areas of the memory. And the low address bits need to come from the D flip-flop, as they specify which line of the character we're on, and I'm going to wire the corresponding inputs there back up to the display controller onto the right pins. We don't need all the other display controller outputs to be latched here anymore because I'm not using them, but I can wire any more back through as and when we need them. For the rest of the character ROM address lines, I need to wire in an ASCII code, and I'm going to go with FIT65, which is the code for capital letter A. From the bottom bit to the top bit, that's 10000010. So the display controller sends the line number to the flip-flop, which holds onto it once per scan line, providing the low address bits to the character ROM, and the higher address bits of the character ROM provide the ASCII code of the character to display. The character ROM looks up the bit pattern for that corresponding line of pixels, and its data lines go to the shift register, which accepts those 8 bits of data and outputs them 1 bit at a time to the display. Let's turn it on then, and we get a screen full of capital A's. The first column here seems to be 1 pixel lower than it should be, but we can deal with that later. As another test, I'll disconnect one of the address lines and wire it high instead, and that's changed the A's into C's, so that's great. It also looks like the right column is getting a bit cut off there, another thing to deal with later. And the top row of pixels is also slightly offset, which usually means there's an issue with the porch size, I think. So just as with the shift register, when we first hardwired the data and then made it use more variable data from the display controller later on, let's do the same for the character ROM. I'll remove the 7 bits that specify the ASCII character here and wire them to the low address lines coming from the display controller. And this should give a more interesting sequence on the screen, and is also another great test to make sure the addressing is working correctly, as it's a lot easier to read proper characters than single pixel binary codes. And powering on, that looks great. It's counting up through all the characters, and they all look nice and crisp and clear. I can see it counting from 0 up. Note that I made these low value characters display as 2-digit hex numbers. And after hex 1F, it moves on through space, exclamation mark, quotes, hash, dollar, and so on. And here, where it gets to the end of the lowercase alphabet, it reaches hex 7F and then wraps around, as I only connected 7 bits. So that's really great. I'm happy with that result, and it only took a few components really: a clock, a PLD, the display controller, a D flip-flop, a character ROM, and a shift register. The quad NAND in there isn't doing anything anymore, I just forgot to take it out. So to proceed from here to a dynamic display that can output whatever the CPU wants, we obviously need to add some RAM. The RAM goes in between the display controller and the character ROM. The addresses from the display controller will feed into the video RAM, and the data from the video RAM will provide the ASCII code to the character ROM. I'm going to leave that for another video though, because in order to set that up we're going to have to arrange for the CPU to be able to write to that RAM, and that's going to require understanding the various bus control modes that the SCN2674 video controller provides to help us out with that. So as always, I hope this has been interesting. I've tried to kind of go through all of the steps required to get to this point. When I'm doing this kind of thing, I do tend to do it a small amount at a time and then test as I go, because then you catch problems sooner in the process and you don't end up with a big circuit that doesn't work and any part of it might be wrong. So I hope it's helpful to just sort of see that process here. And do ask any questions you have in the comments as always. See you next time.